So now that we have some understanding of light or electromagnetic radiation, we're going to shift our attention to another phenomenon that was observed around this same time, and that is what we call emission spectrum, right? So this is the phenomenon that occurs when certain elements or small molecules are energized, they absorb large amounts of energy, they will then, as a result, emit light. And this light is typically of a unique color for that particular element or small compound. So for example, right, neon atoms, when they absorb typically electrical energy is the most common one that we use, they will re-emit that energy as red light, right? And this was the classic type of what we think about as a neon sign here. Now, what you'll notice here is that nowadays these, quote, neon signs can be made in many, many different colors. You see some of that here, and you can make almost any color. This has to do with using other elements in there, right, besides neon. So you can see here simple tubes, which can show some of these. So the first one here is a mercury lamp. So this contains mercury vapor. Again, we're passing electricity through this, and you can see that mercury is emitting a blue light. And hydrogen emits sort of a pinkish light, and other elements will again emit different colors of light. You can also see this phenomenon in something known as flame test. Right? So when you burn materials that contain certain elements, that flame is a characteristic color associated with the element. It's kind of the same idea here that we're observing. So the idea is when you take the light that's given off by these elements and you focus that and you send it through a prism to separate the different wavelengths, to separate the different, quote, colors of light, what we see is what's called an emission line spectrum. Now, two important ideas about this, or a couple important ideas, is that notice it is not a continuous spectrum. Right? So white light, when you pass it through a prism here, gives you a rainbow, right? But the light coming off of these elements is a non-continuous spectrum, right? It only contains certain wavelengths of light. So for hydrogen, we got a wavelength up here in the red, we have some blue, we have some purple, some violet, and you go down here, right? So we have these spectrums. Now, as you can see over here, different elements will give off different characteristic spectrum. And so this line spectrum became known, or became what you might refer to as a way to fingerprint the element giving off the light, because every element, or even compounds that give this off, had a unique line spectrum. Now, the other part of this is why. Right? When this was first observed, it was incredibly confusing, right? Because there was no way to explain why the light given off, right? Clearly we can observe the light given off, but why would it not be white light? What about the element is saying is controlling or is allowing only the emission of these particular wavelengths of light and not any wavelength of light? Why do we not see white light given off by all these elements? That's what all of the science said should happen. Now, that's where we get into our first model of the atom to try to explain this behavior, right? And of course, we're going to look at the electrons, right? That's what these models are. And so this is the Bohr model. So for one key idea here is the idea of quantized energy. So what essentially the Bohr model says is that if you take the nucleus, right? Remember, the nucleus doesn't really do anything. The electrons are outside the nucleus. And so what the Bohr model stated was that an electron could exist at specific distances away from the nucleus. Now, one thing that we have to understand is that the further you are away from the nucleus, the higher energy that electron is going to be, right? Because close to the nucleus is stable, right? Because we have that attraction between the electron and nucleus. So that's low energy. The further you get away, the higher the energy is. So as we move further away, the energy of the electron gets higher. But the key is that what Bohr said was an electron can't be just anywhere out here, right? An electron could exist at here, it could exist here, it could exist here, it could exist here, it could exist here, but an electron could not exist here, right? That's not allowed. So, how does that help us explain our emission spectrum? Well, if we look at what we propose happens during this process, the idea is that when we put this energy in, like electrical energy, what happens is electrons will get excited. So an electron will, for example, jump from level 1 up to, say, level 3. Okay? So the electron's going to absorb some energy, it's going to get excited. Now, that excited state is very short-lived, right? So at some point, these electrons will relax back down. So that electron can relax from, say, 3 to 2, or if we look at one over here, right, an electron that's excited up to 4 could relax down to 3. But the bottom line is, however far it relaxes, right, that's a specific amount of energy that it is relaxing, right? Because remember, each of those distances represents an energy. So if we take the separation between 1 and 3, or the separation between 3 and 4, that's going to be a certain amount of energy. And so when it relaxes, that energy has to go someplace, and that energy is given off as light energy. And if the energy of this light, right, falls within the visible region, right, it's going to occur at a specific wavelength, right? So remember, the energy of this wave is connected to its wavelength, and so every energy here represents a wavelength of light. And since there are only certain energies represented by the spaces between the levels, then only a limited number of energies of light can be given off, and therefore only a limited number of wavelengths of light. And so hence we only observe a certain number of wavelengths of light, not every wavelength. Now, for most of these elements, we're only observing wavelengths that are in the visible region, right? There may be other wavelengths that occur in the UV or the infrared, but the basic premise, it doesn't really matter. The basic premise is that this is the reason why, or the explanation why, we don't see every wavelength, because the energy transitions can only represent certain energy values. Those certain energy values represent certain wavelengths of light that are given off. So, for example, when you have a shorter energy gap, remember, lower energy is going to correspond to longer wavelengths. So maybe the red line corresponds to the relaxation between 3 and 2 here. Whereas a longer wavelength relaxation, say from 5 to 2, is going to have higher energy, right? Shorter wavelength. Maybe that falls over here in the violet region, right? And that's where we get the violet lines that we see. So you can see all of these different gaps. They're going to have specific energies, which are going to be associated with specific wavelengths of light. So to summarize here, the Bohr model helps us understand why we observe these emission spectrums, right? And introduces this idea of quantizing the energy of electrons, or the fact that electrons within an atom can only have certain energy values, not any energy value. Now, of course, the Bohr model was not perfect. It was replaced by a more full quantum mechanical model, one of the big reasons was the Bohr model only worked for single electron systems. So something like a hydrogen atom. Right? It can explain that very well, but it failed to predict the emission spectrum of other elements that contain more than one electron. And so for this and other reasons, it was eventually replaced by a more full, what we call quantum mechanical or wave mechanical model of the atom. And we'll look at that in our next section, our next video.